thank you. Can you hear me? Okay, great. Thank you for sticking it out all the way to my talk. I'm impressed with your endurance. Okay, and you know, I gotta say, it is fantastic to see so many developers here in Northwest Arkansas. I didn't know there was so much talent here, and I'm really excited to see this many people that are that serious about development. So, as stated, my name is Michael Gashler. I teach at University of Arkansas. My passion in life is learning. I love learning. I love helping students learn, and I teach them about learning. So, because I teach learning at an institution of learning because I love learning so much. Today I get to speak about my second favorite learning model, the artificial neural network. Now I word it that way so that you'll all think in your head, what's your first favorite learning model, right? My first favorite learning model is the biological neural network. Why? Well, we all have one. It's located between your ears, and it's very useful. It's the reason you're all good developers, right? I mean, it is, very much. Because we've helped these biological neural networks to learn, you're good at what you do, and this whole conference exists because of that concept. Artificial neural networks are not yet competitive with biological neural networks. If you're worried about the singularity, I can put you at ease now. It's not coming this decade. However, I consider that to be a bug, and I'm working as hard as I can to find that bug, and we're going to fix it. I want artificial neural networks to be as competitive with biological ones. Why? Because we understand artificial neural networks, and if they ever start to do what biological ones do, then we start to understand ourselves. We're starting to figure out what it is to be human, what it is to be smart, and I think something phenomenal is going to happen once we reach that point. So let's start off with a simple diagram of a neural network. It's a square. I show that picture because I want people to know neural networks are not scary. They're squarey. Okay. In a previous talk, Stephen and Luke talked about neural networks, and they talked about how they are function approximators. The idea is numbers go in, and some numbers come out. Now, that's exactly what these things do. They simply approximate some math that we want them to approximate. And we usually equip neural networks with weights. You can think of these weights intuitively as levers or knobs. They're the things that we tune and adjust, and as we adjust them, it changes the function that the neural networks represent. Now, in order to tune the weights of a neural network, we're going to need some data, right? So here's some data. Actually, these are just blue dots I made on a Cartesian coordinate system. They have absolutely no meaning whatsoever. But the idea is that a neural network represents some type of a function, a line, a curve, something that we could potentially fit to data. And the way we do that is we adjust these weights. Now, think with me for a minute. Suppose you didn't know how to adjust the weights because the box was a very scary, complex machine. Could you possibly train those weights in an intelligent manner? I claim that you could, because you could just change them, and one of two things will happen. They might make the model worse, meaning less fit to the data, or they might make the model better. Now, if they make it worse, what do? You put it back, right? And then repeat. If you were to do this in a loop, if only we had a machine that was really fast and could do loops, oh, hey, we do, then we could train the weights of a neural network without understanding what's in the box. And that's the phenomenal thing about neural networks. We don't have to understand them in order to train them. All we have to do is fiddle with the weights until they approximately fit to our data. Why did we want to fit to our data? Yay, we have a line going near a bunch of dots, but what good is that? Why did we do it in the first place? Well, if we have some inputs, we can then use this function. We can feed those inputs into the neural network, and what comes out is the corresponding output that goes with those inputs. Now, that's all good and well, except it's still kind of worthless because what can you do with one number that goes in and one number that comes out? The real power of a neural network starts to occur when we use multivariate. So I'm going to change these italicized letters to bold letters, which represents that they're now vectors. So lots of numbers go in and lots of numbers go out. Now our model looks kind of like this. Much more scary. Now we're starting to get terrified, right? A whole bunch of numbers feed in to these neurons, these artificial neurons, and they're connected by all these lines. These represent the weights that we get to tune. And yes, each one of those neurons is truthfully rather dumb, but when working together, they form a lot of power. Is that not like the companies we all work at? I think it is. There's a lot in common there. But neural networks utilize that power, the fact that they can all do something. When you put it all together, they can do lots of things. For example, what should we do with the neural network? What if we wanted to make an artificial doctor? We might gather a whole bunch of individuals, measure their height, measure their temperature, their body weight, the number of spots on their tongue, whatever types of information we want to feed into this thing to try to give it enough knowledge to make a decision. And maybe we'll use an expert doctor to diagnose what these people actually have. This guy has cancer, that guy is a hypochondriac, this person is healthy and has no problem whatsoever. If we had enough examples and we tuned the weights until the neural network fit these examples, what would we have? Well, we could feed in the symptoms. It would tell us the condition. Is that not an artificial doctor? So let's compare this with humans for a second. If you want a new doctor, you got to send a guy to medical school. It's going to take at least 8 years and several $100,000 of tuition. It's very expensive to produce a medical doctor. What does it cost to make an artificial doctor? Well, we've been working on it for more than 50 years. We've dumped millions of dollars into research, and when the darn thing's done, all it can do is diagnose diseases. It can't put its arm around you, it can't say they're there, and it can't make you feel good. So why did we do it again? Well, there is a significant difference. The first time, the artificial neural network was really expensive, right? But what if you want a second one? If you want a second doctor, well, you got to make another person. You got to raise them for 20 years, which means they need a mother, and a lot of things, or a father, or a guardian, or whatever, however you want to put it. And it's very expensive again. If you want to make a second artificial doctor, you hold down the control key, you press C, you stick your thumb drive in the USB port, you press Control V, you wait for the little icon of the picture going into the other folder, and as soon as the animation is done, you have a new artificial doctor. You could fill up the world with these things instantaneously without any more expense, and that's really the power of it. So yes, we're dumping way more money into this than it costs to make a doctor in the first place, but the fact that the algorithms are entirely reproducible, information has properties that physical things don't have, that makes it all worth it, and that's why we really, really need more artificial intelligence, more machine learning, and the more we understand machine learning, the more we can do this. Okay. This is great. You understand that they're powerful, but so far you're all disappointed with my talk because I said I was going to tell you about non-traditional uses of neural networks, and everything I've said so far you already knew, right? We already know about big data. We know that when you throw neural nets at big data or big data at neural nets, what happens is they fit the things and they make good predictions, and companies have been using this for the last 20 years. It's very effective, but we're all aware of it. I'm going to now start talking about research level stuff, the things that are still in the lab. They're not necessarily being used by everybody, but it's going to give you a picture of where neural nets are going, what's coming out in the future, and how we're getting a little bit closer to making the artificial learning systems a lot more like the biological ones. So, show an example of something that's a little non-traditional. I went to Google, as we all do when we need something. I did a quick Google search for Northwest Arkansas. Please don't lynch me that I did that on purpose. Actually, that's more offensive, isn't it? I actually really appreciate this area of the world. I think it's beautiful, but I mistyped it on purpose. Look what Google did. They didn't take the inputs that I gave them and run it through some function approximator and give me the results. They didn't tell me anything about Northwest Arkansas, because there's no such thing as Northwest Arkansas, right? They gave me results on Northwest Arkansas. In other words, they didn't respond to what I said, they responded to what I meant. Can you think of any case where it might be useful to somehow understand what your customers mean rather than what they say? I think that's a darn useful thing. So, how on earth do they do that? How do they know I meant Northwest Arkansas rather than Northwest Arkansas, which is actually what I said? Neural networks have a certain property that I'll describe. Now, some of you know this. If you've studied neural networks, we don't just tune the weights randomly like I suggested. We could, but it's a little bit slower than an approach called backpropagation. The way backpropagation works is this. We differentiate the models. So, calculus, I know, but calculus actually is useful. If you take the error surface, so this curve that you're seeing here represents how bad the neural network is for different sets of weights. The axes here, you see I've labeled W1 and W2. And the goal here is to try to get to a point where the error is as small as possible. Well, we use an approach called tobogganing. We basically follow the gradient downhill. And by doing that, we minimize the error function. In other words, it tells us how to tune the weights. So imagine we not only have knobs, but we have a magical little fairy that tells us, turn this one to the left and that one to the right. And if we turn it in the direction that it says, our neural networks get better. That's cool. Everybody understands that. But here's what a lot of people have missed. It turns out, if a model is differentiable with respect to its weights, and neural networks are, because that's how we train them, then they are also differentiable with respect to their inputs. That was a really subtle change. I just changed those W's to X's. But what that means is I can change the inputs until something sensical comes out. So Google can modify my query until it makes sense. And that, it turns out, is a surprisingly powerful little property of neural networks that other learning algorithms don't have and can be used in many different ways. Let me show you some examples. So these are a bunch of handwritten digits. They actually come from a data set called, I call it MNIST, M-N-I-S-T. I think that's pronounced correctly. Usually the way MNIST data set is used is they feed the images into the neural network, and they have the neural network predict what digit we're looking at. This is optical character recognition. In 2007, I attended a conference where Jeffrey Hinton was presenting a neural network for doing that. And I thought, boring, just OCR. And I walked right past his booth. Turns out that was the start of the deep learning revolution. And I kind of missed it, but hey, I caught up a little bit later. I decided to try something a little different with the same data set. Instead of feeding images in as the features or the inputs, I decided to tell the neural network to predict the images. Now, you think about that for a minute. That's asking a lot of a neural network, right? I'm saying, hey, use your creativity, do what a human does, produce a picture of handwritten digits. And now question, what do I use as the inputs? Well, I didn't know. So I just picked some random numbers, fed them in, and said, here, produce a digit. And I let the neural network adjust those inputs. In other words, the neural network had the power to use whatever inputs it wanted, but it had to produce digits because I forced it to use the digits, and I tuned the weights until it produced things that look like digits. Here's what my neural network produced. These are a whole bunch of number 4s. Now, you're not that impressed because a human can draw 4s, and that's easy, right? None of these 4s were in the training data. These 4s were all generated by the creativity of an artificial neural network. But what I think is more significant is look at how they're arranged. If you look on the horizontal axis, you'll see that all of the 4s along the left side have a pointy top, and all of the 4s on the right side have an open top, right? So I call this top openness. I don't know what exactly that means. If you look along the vertical axis, along the top we have all the digits that are upright, and on the bottom they're all sort of italicized or slanty. Now if you think about what's important in a 4, the number 4, how would you write a 4? What types of variations are there? I don't know, but these are the ones that a neural network identified after seeing a whole bunch of examples of handwritten 4s in no particular order. It just decided of its own accord to arrange the inputs in this manner to create the concept of top openness and top slantedness. Now, does it understand? Can it see the 4? Does it feel the meaning that we get from a 4 when we see a 4? I don't know. But here's what I do know is it decided that slantiness and top openness are the important things going on in this data set, and it arranged them in that manner in order to make sense of itself. That seems kind of like the way we start to understand things. This is no longer just recognizing, oh, that's a 4. It's recognizing it's a 4 and it's this much slanted and it's this much top openness and how varied it is. If I had given it another dimension of input, it might have used it for boldness or for whatever other properties of the 4s existed in that data set. But the neural network seemed to sort out what was actually there. And I think that's, at least at a conceptual level, it seems kind of significant. If a machine is starting to understand what it's looking at, what can we do with that? Let me show you some results that were actually produced by NVIDIA. These are not my results, so disclaimer there. These are a whole bunch of pictures of celebrities. Exactly half of them are pictures of celebrities. Exactly half of them are people that do not exist. These images were created entirely from the imagination of a machine. So let me give you just a second, answer this question. Which of these faces are real, and which of these faces are synthetically generated by a neural network? That's difficult to tell, isn't it? Well, here's the answer. All of the people on the bottom row are real human beings, and those are photographs. Every single one of those pictures along the top row does not exist. And in fact, what they did is after the computer generated those images of very realistic looking people, we found the most similar, well, not we, NVIDIA, found the most similar image in its training data that the neural network was shown, and that's the face you see beneath the image above. So in other words, there are no people that look closer to that person on top than the one you see, at least according to some metric that they used. Now, that's good enough. That's starting to deceive human beings. What can that do when a machine is creative enough to produce something like that? I can paint a picture, but I can't make it so realistic that people are going to think it might be a photograph. In many ways, neural networks are starting to exceed the creative capabilities of humans, if not, well, that's a very loaded way to put it. They're able to exceed our ability to produce things that seem realistic. Let me show you something I did in my lab with the same technique. And again, I'm just using the same technique of allowing the neural network to adjust the inputs. It's not really a very dramatic difference to neural networks, but it's a surprisingly powerful little feature. This is a picture of a warehouse. I took a virtual robot and drove it around through this warehouse. And here's a plot of the path that I followed. Now, if you look at this picture, you'll see that color represents time. So my robot started where it's red and then drove through orange, yellow, green, blue, purple. And it drove around for a long while. It was actually controlled randomly, so the robot was just going all over the place. There was obviously an obstruction in the middle, so the robot didn't go into the middle. But you can kind of see that it rather thoroughly sampled the space, right? While this robot was training, I withheld all information about its location from the robot. The only thing that it was able to see was an image based on a camera that it could use. Now, giving the robot just the images, no other information about where it was, I gave the robot 2 input values to work with. Using those 2 input values, I said, okay, use your neural network and predict the image that you're seeing. So I trained the image from its camera to the image that its neural network was trying to predict. I matched them up, and the difference between it is how I adjusted the weights. Here's what the neural network produced as the inputs that it wanted in order to generate the images that it saw. Now, if you look at that, you'll see they're not exactly like the picture on the left, right? It's oriented differently. The lines aren't perfectly straight. There's all kinds of problems with it. But at a high level, can you see what's going on? Essentially, this neural network knew where it was. And how did it know where it was? I didn't tell it where it was. All I did was show it a bunch of pictures. And I didn't give it a lifetime of experience. I didn't tell it even what direction is. It has no concept of latitude and longitude. It didn't even know direction was a thing. All it knew is it needed to reproduce these pixels that it could see with its camera, and it could adjust its inputs as needed to do that. And what it did is it reproduced these numbers, which map quite obviously directly to the inputs that I actually withheld from it. After I did this, the neural network had the ability, given its location, to visualize, imagine, or dream, if you will, what it would look like to be somewhere. So in its imagined space, so I did this now entirely in simulation, not in my virtual robot. I drove the robot through a path in that space of its imagination. In other words, in the inputs that it had created. And this is highlighted in blue. This is the path that I took the robot through. Now, note that I didn't actually do this in the real warehouse yet. This was just in simulation. I could see on the screen these blurry pictures on the bottom of where I was, and I could actually navigate through the warehouse in the imagination of the machine. Now, I gotta confess, I kind of misled you a little bit. Those pictures along the top were not actually generated. Those were not actual pictures from the camera of the robot that were used to train the robot. Those images on the top were images from the camera of the robot after I had made this plan. So let me repeat that in different words. I drove it through this sequence that you see in those bold blue dotted lines, only watching the images along the bottom. Then once I had made the plan, I executed it in the real warehouse, and those pictures along the top are what it actually saw. So this robot doesn't even know what a stack of bricks looks like, but can you see how the images on the top look just like the images on the bottom? And when I say just like, I mean they're different, but they're close enough that you can tell when it was in the same spot. Turns out that the robot's imagination was sufficiently accurate that it could wander through the warehouse, and then when it did it for real, it actually saw the same thing. Now, suppose you were to close your eyes and walk over to, say, the bar and grab a snack and then come back to your seat. Imagine the pictures that go through your head as you're doing that. Are they sufficiently accurate that you think you could line them up side by side with what you might actually see if you were to perform it? I think probably not, and that kind of suggests that neural networks are starting to develop capabilities that are surprisingly precise. And when the singularity does come, I fear to imagine how precise they could possibly be. If a machine is starting to understand its external environment, let's do a little thought experiment. Suppose you have a robotic vacuum. I do, and I believe my robotic vacuum is aware of its external environment. Here's why I believe that. It used to crash into my piano a lot. Now it doesn't. It just kind of navigates around the piano. Therefore, it's responding to its environment. It must know about it. It has a model inside of its head. It's pretty much aware. How long can a machine be aware of its external environment before it starts to include itself in its own model? And when that happens, do we not have self-aware machines? I think that's pretty cool and pretty exciting because we as humans brag about how we're so self-aware and machines are not, but what is really the difference? Let me talk now about different patterns, different models that we're starting to see with neural networks in research. So the first one I want to highlight is the function approximator. This is the one we've been studying for 50 years. Everybody knows about it. You all use it with big data in business. You train it to fit to your data, and it predicts outputs based on your inputs. This is the model I've mostly been using so far, except that I've used this extra trick of also adjusting the inputs, which means even this model hasn't yet produced all of the things that have yet to come from it. There's still more that function approximators have to offer. There's another model that is also quite old, but it's starting to become very popular in the lab, called the autoencoder. An autoencoder utilizes two neural networks, and what they do is they try to predict the same thing that you feed into them. So I show it a picture of a banana, and I try to make it generate a picture of a banana, but I pass it through an intermediate encoding. What an autoencoder specializes at is understanding things. It's going to try to reduce things into a meaningful summary, a meaningful representation, and we call this the encoding. I've represented that with the letter V here. And then it tries to decode it back into the original image that it's represented. A lot of progress has been made in autoencoders recently, and what that's doing is it's meaning that machines are now able to understand what they look at. We're able to get very small descriptions of very high-level, very complicated, meaningful concepts. Here's a model called an actor-critic model. These are really useful for driving robots, for playing video games, any concept where there needs to be some control. They're being used a lot, but so in Berkeley, they have a laboratory that's working a lot on laundry folding. They're used in video games. There's a video game called Dota. Has anybody played that? There are professional Dota players. World professional Dota players were recently beat by OpenAI's implementation of an actor-critic model, which just shows these things are pretty darn impressive. More impressive than humans at playing complex video games. Recurrent neural networks are also a very old model, but they're starting to really surge ahead in the lab. We've got LSTM networks, and a lot of improvements have recently been made to recurrent neural networks that have enabled us to understand time series models. Anything involving temporal data, anything that changes over time. If you want to know market forces, customer responses, things like that, anything that's influenced by time, recurrent neural networks are very powerful at doing that. There's another model called a generative adversarial network. Anybody heard of those? This is the model that was used by NVIDIA to produce those celebrity faces that I showed earlier. This model is very good at creating things, at generating things out of the blue that are very convincing and that follow rules that please humans or that look like they're on the manifold of reasonable predictions. Essentially, they're performing a job of creativity. Now, if you start to look at these various models that are getting really hot in research, a few things tend to stick out. One is, hey, we're doing different pieces of the human brain, are we not? Aren't these the kind of things you do when you're running through daily life at work? You're doing some of these different functions. The other thing is look at the inputs and the outputs of them. I've labeled the common ones with similar letters. Let me highlight them a little bit more. A lot of these pieces are the same. That is, the inputs to some of these models are the internal parts of some other models or the outputs of some other models, which strongly suggests that they all fit together somehow. If we do put them together, we arrive at something that's called a cognitive architecture. So one of the new buzzwords in neural networks these days seems to be cognitive computing. It basically means you take a bunch of learning models and piece them together in order to perform some of the thinking constructs that are occurring that are probably analogous with the thinking constructs that humans do. Why do we employ humans? Because they're smart, because they can do useful stuff, right? Well, to a large extent, neural networks are starting to achieve cognition that's somewhat comparable with the biological neural networks that sit between our ears, and I think that's kind of cool. This particular cognitive architecture you're looking at here is one that I published. One thing that I thought was really fun is as we started studying the brain and how it works, recent discoveries have found that many algorithms performed in the actual biological neural networks are following the same patterns that we've independently discovered for cognitive architectures. I'd enumerate it, but I'm a little short on time, so let me just speed on. How close is this getting to reality? Well, we don't have an implementation of a human brain. We're not going to have one anytime in the near future. The human brain is a very complicated machine. We do, however, have a full simulation of a very, very simple life form. This is a C. elegans nematode roundworm. Actually, it's not. It's a simulation of a C. elegans nematode roundworm. You could take a look at this at openworm.org, something like that. They have built an entire simulation of a life form, and it behaves just like the life form. Now, it's not a very smart life form, so maybe that's not that cool, but we are starting to do a lot of rather smart things with neural networks in the lab, and I think that's pretty exciting. In conclusion, neural networks can do a lot of stuff. If you don't know some of the features, you can simply adjust the inputs. You can adjust those features until the neural networks thinks they make sense. That's a very useful thing to do for various reasons that I showed you today. If you are missing labels, meaning you don't know the outputs, neural networks can train just fine with missing outputs. If you don't know what activation function to use, if you don't know what neurons to use, if you don't know what's inside of the neural network, it kind of doesn't matter because they're auto-adaptive. Neural networks train themselves, and the algorithms that we use to modify them pretty much work with whatever you give them. And that's what makes them super powerful. If the data isn't available all at once, neural networks are incremental. What I'm kind of trying to get at here is neural networks have the properties of brains. There's a reason we hire humans, and there's kind of a reason you should probably be using neural networks as your learning algorithm of choice. They fit to whatever problem you've got, if you know how to make them fit to that problem. Finally, if you have no error signal, you can back-propagate them from a downstream model. What that means is you don't actually even need examples of what the neural network's supposed to do. If you start hooking them together into these architectures that try to achieve cognition, neural networks can actually adapt to give the downstream model whatever they need to accomplish their job better. It's almost like a human that's trying to work to satisfy the demands of a boss who's working to satisfy the demands of somebody else who's working for the customers. Neural networks work together kind of like entities in a company, and that's what makes them extremely powerful. So anyway, there's a teaser on what's coming with neural networks, and thanks for attending.